Good afternoon from the annual meeting in San Diego. We're pleased to be here with Dr. Scott MacRae. Thank you, Scott, for being with us this evening.
Thank you, Jonathan.
Scott, I know that you have a really interesting presentation at this conference about a great technology called LIRIC, which is a disruptive refractive technology, if you will. Tell us a little bit about how it works and what some of its applications may be.
Well, LIRIC is a low energy, pulse energy femtosecond treatment where we can actually change the refractive index of the cornea, intraocular lenses, or even contact lenses. The advantage of it is that it's relatively non-invasive. We've been working on this project for almost 15 years and worked first in animals, and now we're excited about being able to present our first in human data as well in cornea.
Well, tell us, Scott, a little bit about how this works. What is the mechanism by which you're inducing refractive change, and how do we go about measuring that?
So we've worked first in cats. We can actually do wavefront in cats and follow those cats out for over 2 years, basically doing several diopters of correction with it, and it's relatively stable. So then we've done extensive safety studies as well, and we'll present that at the Innovators Lecture as well. Basically we find that it's relatively non-invasive. We're using energy levels about 1/60th to 1/400th that we use when we actually create a LASIK flap. So it's very, very low energy, but we can actually change the refractive index of the cornea rather than changing shape. All the other techniques that we use, glasses, contact lenses, intraocular lenses, or corneal refractive laser surgery, they're all changing shape. This is fundamentally different in that it's changing the refractive index of the cornea, or an IOL, or a contact lens.
So when we talk about changing the refractive index of the cornea specifically, is it changing the refractive index of the entire cornea equally, or is it picking sort of a specific layer within the stroma that's then altering the total refractive power?
Well, we can treat, like in the first in human studies, we treated at 240 nanometer or 240 micron depth, and it's a very thin area that's actually affected, probably about 10 or 15 microns thick. Mm-hmm. So it's a very small area in terms of the corneal thickness, and you can actually go back and do multiple treatments based on what we learned from contact lenses and intraocular lens implants.
And I know, Scott, that it seems like you've looked at the local cellular area around the band of treatment to see whether there's any adverse local cellular reaction. And what have some of your findings been there?
So in terms of corneal nerves, we actually just reported this at last week's ARVO meeting. Basically, we looked pretty extensively at corneal nerves and found that there was no significant nerve damage, and which is pretty exciting. So the dry eye potential could be remedied. We also looked at the actual pattern that it creates in the cornea. And what happens is that it condenses collagen. Basically, the type 1 collagen is clustered in the areas where we do the refractive indexing. The water kind of disappears, basically, and as a result of that, you've densified the cornea, increasing the refractive index.
Well, that's a really fascinating way to look at it, and it's really important to know that structures such as corneal nerves and keratocytes in the area are not adversely affected. What kind of range, Scott, do we foresee being able to treat with this type of technology? I know that in your human studies you looked at some specific corrections, including presbyopic corrections. Is that right?
Yeah, we did a 2.5 diopter presbyopic correction with an 80% distance, 20% near correction in our first in human studies. That's it's a mild treatment, and so but we'd like to go on. Our next step is basically doing sphere and cylinder treatments. Those will be more convincing in terms of getting a stronger treatment and a stronger treatment effect.
Well, Scott, this is a really exciting technology. I'm so glad you're presenting it at the Innovator section at this meeting, a really exciting way for us to consider refractive treatments without disrupting the corneal surface or the corneal nerves. This is a great technology, and thank you so much for presenting it today.
I really appreciate it.
And
thanks, Jonathan.
Thank you for our viewers at home for your support as well. Good afternoon.
Thank you.